We're going to start our year with a review of right triangle trigonometry. Trigonometry is a branch of mathematics that deals with the relations of sides and angles and functions that depend upon angles. Our study is going to begin with trigonometry that concerns right triangles. And you'll remember this from geometry. In a right triangle, if we look at an angle theta that is not it's not the 90-degree angle in the triangle, the side opposite is noted. The leg that is adjacent to the angle theta is noted, and the hypotenuse is noted. Remember that the hypotenuse is always across from the right angle. So the adjacent leg is different from the hypotenuse. In a right triangle, if you look at one of the acute angles, not the right angle, sine of that angle, so sine of theta, which is a Greek letter that we use in trigonometry frequently, sine of theta is equal to the opposite side over the hypotenuse. It's just a ratio of those two sides. Cosine of theta is equal to the adjacent leg of the right triangle over the length of the hypotenuse. And the tangent of theta is, tangent of theta is equal to the opposite side length over the adjacent leg length. And we remember this with the mnemonic device SOHCAHTOA. All right, so if we want to find a trigonometric relationship for each of these right triangles, we're going to be looking at sine of angle P. So when we're dealing with sine, we need the length of the opposite side, and we also need the length of the hypotenuse. Now, in a right triangle, usually we give the letter C to the hypotenuse. Notice that C is not given in this right triangle, but we can figure it out. So we're going to use the Pythagorean theorem here. A squared plus B squared is equal to C squared, where C is the length of the hypotenuse. So 4 plus 9 is equal to C squared. 13 is equal to C squared. And that means that C must be the square root of 13. We're going to leave that in exact form as a radical. And then we're going to find the sine of angle P, which is the length of the opposite side over the length of the hypotenuse. And then we'll rationalize that. That'll become 3 times the square root of 13 over 13 is the value of sine of P. Watch out for a pitfall. Students often write that sine of angle P is 3 over x, saying, well, I don't know what x is, but you can figure out what x is. All right, so in the next example, tangent of angle C, let's take a look at angle C here. Tangent is the value of the opposite over the adjacent side. And let's give the letter B for our adjacent side. And again, we'll have to use the Pythagorean theorem. So 1 squared plus b squared is equal to the square root of 10 squared. So 1 plus b squared is equal to 10. That means that b squared is equal to 9, and b must be 3. So the tangent of angle C is equal to the opposite side over the adjacent side, which is 3. Whoops, let me fix that. No rationalizing to do with that on that one since we don't have a radical in our denominator. All right, let's check out example 2. Cosine of angle X is equal to 3/5. Now you'll notice in this triangle we have an angle X, and opposite angle X we have side X. So uppercase X is the vertex and lowercase x is the side length. The same is true about Y and Z. Opposite the vertex is the side length of the same name with a lowercase letter. All right, so if cosine of x is equal to 3/5, we know that 3/5 must be a ratio of the adjacent over the hypotenuse, since SOHCAHTOA, cosine is adjacent over hypotenuse. And that can mean that our adjacent side is 3 and our hypotenuse is 5. So if we're talking about angle X here, our adjacent side could be 3 and our hypotenuse, y, could be 5. Now, if I use the Pythagorean theorem, 3 squared plus x squared is equal to 5 squared, because 5 is the hypotenuse. That's going to give us 9 plus x squared is equal to 25. Subtracting 9 from both sides, x squared is 16, and x must be 4. That's the famous 3, 4, 5 triple that you may remember from geometry. And so one possibility for our x, our y, and our z is x is 4, y is 5, and z is 3. So let's list a couple other possibilities, though. If adjacent over hypotenuse is 3 over 5, adjacent over hypotenuse could also be 6 over 10. Those are the same fraction, 6 over 10 and 3 over 5. So we could very well double the value of all the sides, and the ratio would still be the same. So 8, 10, and 6 is another possibility. If we want to multiply the sides by 3, we can do that. So 4 times 3 is 12, 5 times 3 is 15, and 3 times 3 is 9. We could also divide the sides. We're going beyond what the question asks here, but suppose we took the 4, 5, and 3 and we divided them all by 5. 4 fifths, 5 fifths is 1, and 3 fifths. So there's lots of different possibilities that you could have for those side lengths. Adjacent and hypotenuse don't have to be 3 and 5, but they can be. All right, let's check out another example. Sine of angle D is equal to 3 times the square root of 2 over 5. And in this triangle, side E is 5 times the square root of 2. We're supposed to find the missing side lengths, D and F. So one of the things that we notice is that we're talking about sine of angle D. Well, let's check out angle D right here. So sine of angle D is equal to, and sine would be the opposite, which would be our D, over the hypotenuse, which would be our E value. 5 times the square root of 2 is the hypotenuse. So that's the sine of angle D. However, we were also told that sine of angle D is equal to 3 times the square root of 2 over 5. So if that's true, then D divided by 5 times the square root of 2 must also be equal to 3 times the square root of 2 over 5. That's a nice proportion. We can cross multiply at this point. 5 times D is equal to 5 times the square root of 2 times 3 times the square root of 2. Be careful here when you're multiplying your radicals. 5 times 3 is 15. Square root of 2 times square root of 2 is 2. So 5 times D is equal to 30, and D is 6. There's one of our sides. And if we have two sides in a right triangle, we can figure out the third side by using the Pythagorean theorem. So using the Pythagorean theorem, f squared plus 6 squared is equal to 5 times the square root of 2 squared. Since 5 times the square root of 2 is the hypotenuse, that must go by itself on one side of the Pythagorean theorem. F squared plus 36 is equal to, and let's do a quick square on 5 root 2. 5 times 5 is 25, and square root of 2 times square root of 2 is 2. So f squared plus 36 is equal to 50, and that means that f squared is equal to 14, and f is equal to the square root of 14. So there are our two missing sides. Here's one for you to try on your own. Pause the video while you're doing this one. Here's the solution to the try this. Notice that you don't really have to cross multiply here, since b over 3 was equal to a whole number 2. You could just multiply both sides by the square root of 3. All right, let's move on. We can use trig ratios to solve for missing sides or missing angles. And so if the trig ratio is evaluated with a calculator, however, this generally produces an approximate decimal results. Exact answers are actually going to be our preferred answer, so it'll be in terms of a trig function, and then we'll have what's called a calculator ready answer, and that means that we can then put the answer into our calculator and then round at the very end. We want to avoid rounding in the middle of a problem. All right, let's check out example 4. Use a trig ratio to write an equation that relates the indicated side and angle measures in each triangle and then solve for each variable. So we're going to first write an equation. And so what we'll notice about this 37-degree angle is that we have noted a variable in the opposite side, and we have a side length for our adjacent side. So that means we're going to use a tangent ratio. So tangent of 37 degrees is equal to opposite x over adjacent 2. Now we have an equation that has the variable x in it, and we can solve for x by multiplying both sides by 2. So 2 times tangent of 37 degrees, and you don't have to write the times sign there, is equal to the value of x. That's what we call a calculator-ready answer, and that's all we're going to do for now. All right, let's try b as well. So taking a look at our 59-degree angle, notice that 5 is in the opposite position, and k is the hypotenuse since it's opposite the 90-degree angle. That means we're going to use a sine ratio. So sine of 59 degrees is equal to opposite over hypotenuse. Now in this case, we can't isolate k by just multiplying by 5 because the 5 isn't doing the dividing, the k is. So we're going to clear the fraction first by multiplying both sides by k. So k times the sine of 59 degrees is equal to 5. And then in order to get k by itself or solve for k, we're going to divide both sides by sine of 59. So k is equal to 5 divided by the sine of 59 degrees. Notice that this produces a slightly different looking result from A. So be careful about these two different setups. Now we can also use inverse trig functions if we want to find the angle. So we're going to do this the same way. We're going to set up a ratio, and then we're going to use an inverse trig function to find the value of the missing angle. So in example 5, we have missing angle A, and 3 is the adjacent side, and 5 is the hypotenuse. So we want to use a cosine ratio. Cosine of angle A is equal to the adjacent 3 over the hypotenuse 5. And now we need to find the value of the missing angle A. That means we need to undo cosine. Remember, cosine isn't multiplying here. Cosine is a different kind of a function. So we need to undo cosine. So that is, if we want to find the measure of angle A, we undo cosine by finding the cosine inverse of 3/5. Do be careful as you write this. Cosine inverse needs to go on the left side of 3/5 for proper notation. All right, let's check out B. We have missing angle P. Square root of 7 is in the opposite position, and 4 is in the adjacent position. It's adjacent to angle P, but it's not the hypotenuse. And so that means that we are going to use a tangent ratio. Tangent of angle P is equal to the opposite value over the adjacent side length. And again, we can find the measure of angle P here by undoing the tangent. Remember, it's not multiplication, so we're going to undo it by writing tangent inverse of the square root of 7 over 4. Remember again, tangent inverse goes on the left side of square root of 7 over 4. All right, try A here first. Pause the video while you're doing this. Here's the solution for A. Remember, we had to clear the fraction first before thinking about solving for x. Now try B, and remember in B we're looking for the angle, so this one's going to work a little differently. Pause the video while you do this. Here's the solution for B. Notice that I put parentheses around the 3. You don't have to necessarily do that. Your calculator will do that automatically if you enter it. So that's something that you can have there, but if it's a very simple expression, like one single term like 3, we don't have to have the parentheses there. All right, let's check out something else here. The triangle below is not a right triangle. However, we can use trigonometry to find the height of the triangle by using a right triangle that you see in the picture. So we're going to find an expression for h, and then we're going to use it to write an expression for the area of the entire triangle. All right, let's take a look at our figure here, and we want to be aware that here's a right triangle that appears sort of in the middle of the big triangle. And we need to use a right triangle if we're going to use SOHCAHTOA. SOHCAHTOA is not valid for any other kind of triangle. So in this triangle, 65 degrees has h opposite it, and in that yellow triangle, 8 is the hypotenuse. That implies that we're going to use a sine ratio. So sine of 65 degrees is equal to h the opposite over 8 the hypotenuse. We can solve for h by multiplying both sides by 8. So 8 times the sine of 65 degrees is equal to h. There's our expression for h. That's one of the answers. Now we're going to use that expression to find the area of the entire triangle. Well, our entire triangle has an area that's equal to 1/2 times base times height. And the base of the entire triangle is 12. And our height is 8 times the sine of 65 degrees. We do have some simplifying that can be done here. 1/2 times 12 is 6, times 8 is 48. So we have 48 times the sine of 65 degrees in simplified form. And that would be the exact form, or the calculator ready form. If we wanted to know either of these and round them off, we can put either of these expressions in the calculator. All right, here's one for you to try below. Notice that, again, you have to find a right triangle, and this time you might find the right triangle in a slightly different place. So pause the video while you try this one. All right, in this one we were asked only for the height. Of course, we could find the area if need be, but we're only asked for the height, and the height is found by looking at this triangle that is exterior to the triangle. This is an obtuse triangle, so its height is found outside the triangle. All right, let's check out some word problems in trigonometry. It's kind of a quick review of all the things you learned in trigonometry when you were taking geometry. All right, so trigonometry can be used to find distances indirectly. That is, by using a known distance and an angle that's measured. And we call those angles angles of elevation or angles of depression, depending upon whether you're looking down. Recall that in one side of an angle of elevation or depression is always, always, always a horizontal line. And I say always and emphasize that because that is the most common error that students make when working with angles of depression or elevation. So in example 7, we have a plane that's flying at an altitude. That means a fancy word for height, right? So our height is 5 miles above the ground. And it is approaching the runway here. There's the path of that plane as it is approaching the runway. It's descending at an angle of depression of 12 degrees. So that means that the angle is measured from the horizontal. Now you'll notice that that angle's not inside of the triangle. We can do a couple things with this. Verticals and horizontals, we assume, meet at right angles, although that may not be true if the ground's not perfectly level, right? But we make that assumption when we're working word problems. And if you consider that the two horizontal lines, the ground and the line of sight of the plane if it's looking straight ahead, are parallel, then those two angles are both 12 degrees because they are alternate interior angles. So that 12 degrees that I drew in green there is the angle of elevation if the runway is looking up at the plane. So the angle of elevation and depression are different locations, but they have the same measure. All right, so what else do we know? We are trying to find the distance directly from the plane to the runway. So the distance directly from the plane to the runway is that straight line distance. So let's call that x. That x is in the hypotenuse position, and h is opposite that 12-degree angle. So that means that we can use a sine ratio. So sine of 12 degrees. Whenever you say sine, cosine, or tangent, by the way, it's always, always, always followed with an angle. Sine of 12 degrees is equal to 5 over x. We're going to clear our fraction. X times the sine of 12 degrees is equal to 5. Now we have to divide by sine of 12 degrees. So x is equal to 5 over the sine of 12 degrees. And since we need to be consistent, that's a measurement that's going to be measured in miles. We won't always have units, but we will usually have units where word problems are concerned. And there we want our units of length to be consistent. All right, let's check out a last example here. At a certain time of day, a student who's 5 foot 3 inches tall casts a shadow 8 foot 4 inches long. So here's our 5 foot 3 student, and here is her 8 foot 4 inch long shadow. We'll assume that our student is standing vertically from the ground, so there's a right angle there. And we are looking at the angle of elevation of the sun. I'm going to call that theta. That's the angle that we would be looking up at the sun from if our face was on the ground there at the tip of the shadow. All right, it's going to be easier for us if we just convert these to inches. So 5 feet is 60 inches plus an extra 3 is 63 inches. 8 feet, 8 times 12 is 112 inches, plus our extra 4 is 116. And so, what are we going to use here? It looks like we've got our opposite and our adjacent sides. We don't have that hypotenuse because the hypotenuse is the line of sight. So sine of angle theta is, oops, made a boo-boo there. Opposite and adjacent implies we are using tangent ratio. So tangent of theta is equal to 63 over 116, opposite over adjacent. And the angle of elevation of the sun is theta. We'll have to do that by undoing the tangent function, and that means we're using the inverse tangent function. Remember, inverse tangent goes on the left side of the expression. So inverse tangent of 63 116ths, as we're reading from left to right. And that's it for our first lesson of the year. On to special right triangles and circular trigonometry next time.